All right, so we're here to talk about buoyancy. Now let's first start with what is buoyancy. Have you ever wondered to yourself, why does a rubber duck in the bathtub float? Or why does a balloon in the air start to rise when it's full of helium? These are the questions that buoyancy can answer. Now buoyancy is based fundamentally around Archimedes' principle. Archimedes found that when you displace a volume of fluid, that the force from the rest of that fluid that was supporting that section of fluid can then be applied to the object that now occupies that space. Using our original model from class, we can start to develop an understanding of why this happens, but we're gonna have to make some tweaks. The original model from class, we found that Newton's second law shows that the net force on an object is equal to its mass times acceleration. Now we're looking at objects that are occupying a volume of space and have a specified density. We don't see that in our original equation, so we're gonna have to make some modifications. We can prove that mass is equal to the volume times the density using a quick unit check. We can see that mass is equal to kilograms, volume is equal to meters cubed, and we know that density is the amount of mass per amount of volume. So if we're canceling meters cubed with meter cubed, we get kilogram is equal to kilograms. So we can rewrite our net force as our volume times our density times our acceleration, which in most cases is going to be gravity with buoyancy. Now, we also can adapt our free body diagrams to understand what's happening. Traditionally, we've been looking at free body diagrams that include either tension forces or normal forces off of objects such as this box. In these circumstances, we're not looking at fluids, but rather we're looking at solid objects being pulled or pushed on by either physical objects or forces that are being applied from something such as a rope. Now let's define a fluid before we get any further. A fluid can be either a liquid or a gas. This is really important because in buoyancy, we can use this principle to be associated with both gases and liquids. Now what is happening? When we submerge a block into some fluid, let's say this is a liquid, if this block is floating, we can say that the density of the fluid is greater than the density of the object. If this wasn't the case and the density of the object was greater than the density of the fluid, the object would begin to sink. Now in our diagram here, we can see how this displaced volume of this liquid occupied this amount of space. Now, the other liquid around it had to be supporting that volume with some force. So we can represent that with these tiny arrows just to get an idea of what is happening. By looking at this, we can see that since all of these points are at the same depth, knowing that pressure slightly changes with depth, these arrows will all cancel out because they're equal and opposite. This relates back to our original model, which we already knew. Further, we can see that the bottom of this box is being supported by a normal force that was supporting this volume of water. And because this block is floating, we know that the total of this upward force has to be greater or equal to our downward force. Actually, we know it's equal because this block is stationary. Now, what are some limitations of our new model? Our new model is accounting for density and volume of the object, and it's looking at liquids and gases, but it doesn't fully account for pressure change when we're simply looking at the force, buoyancy, is equal to the volume of the fluid displaced times the density of that fluid times gravity. Further, it doesn't account for deforming objects. As pressure goes up, we know that the density will increase, and as the pressure is increasing, as it goes deeper and deeper into a fluid, typically represented in our world as lower altitudes. This can cause the volume to shrink, the density to increase, and then for the object to have different relationships with the fluid, thus it could become stationary instead of keep going down. Lastly, a limitation of our model is it can't account for when other things than the fluid are being applied to the object. In this example, if we put a flat surface under part of this block, it completely changes what's happening because now we have an additional normal force, which our equation does not account for. So to recap, we took our original model of Newton's second law, we took our F equals ma, and we reworked it with m equals the volume times density, And this allowed us to show that the buoyant force is equal to the volume times the density, both of the fluid, times gravity.
Okay, so here are the equations that we're going to be using. So first we have a pressure equation, which is pressure equals rho times gravity times height. Then we have pressure equals force divided by an area. This can also be represented unit-wise as newtons divided by meters squared. Next we have our force of buoyancy, which equals the force of a fluid affecting an object going up towards the surface, and then minus the force that is pulling the object down through like pressure, which we talked about up here. And then here, this is just an application of these two equations and this equation combining, so then we can have like a more applicable equation with just more variables. Here we already talked about it in the earlier section, but it's just mass equals volume times density. Here we also have an F buoyancy equation, but now we're just looking at it in terms of volume rather than area times the height of something. So it's also in the same units. And then here we just manipulated this equation to relate how densities are essentially saying that like how the densities of an object in a fluid affect the percentage of that object being above or under the water. And then here we're just doing a unit check. So first we're just looking at the units of pressure, which is newtons over meters squared. Here we have, we're just checking if our units check out for the force of buoyancy. And so we also were able to determine that it was kilograms meters divided by seconds squared. Yeah, and then here we're just defining like what each of these are. So P equals pressure, rho equals density, G equals gravity, which would be 9.8 meters per second squared on Earth. And then we have height, force, area, mass, volume. And this is just representing like a balloon. And then like the force that's pushing down in the air, and then the force that's pushing it up. And then the difference between them would be buoyancy. Okay, so we have this balloon, and in this situation, we can use the equation F net equals F of buoyancy minus F of gravity. If F net is 0, then that means it's stationary, because we know that all the forces even out, there's no acceleration in the system. Then we have if F net is greater than 0, then we know that the object is going to be moving upwards or accelerating upwards. And then if F net is negative, then we know it's going to be sinking. So in water, that would be like if a boat had like a high enough density and then that caused its buoyancy to be too low or lower than gravity, then it would sink in water.
So now let's take all of these new models and formulas that we've been building and let's apply it to a real example. So why don't we do a boat? A good way to abstract the shape of a keel of a boat would be to do a triangular prism with an equilateral triangle. That means that the volume is going to be equal to the length of the boat times the base times height divided by 2. We can write that there, L times AH over 2. And then we know that the density of water is a given value, which happens to be 1,000 kilograms per cubic meter. From our equation for density, that's mass over volume, we can then determine the mass of the amount of water that is being displaced by the boat, or the mass of the amount of water that would be displaced if the entire boat was submerged. In order to do that, we're basically plug and chugging with these equations. we have a given length for our boat, we have a given base and a given height, and we can determine the mass of the water displaced by calculating through all of this. We get 5,000 kilograms. That means that if the boat were to be completely submerged in the water, there would be 5,000 kilograms worth of water that had to be pushed somewhere else. And this is key to understanding whether or not the boat will actually float. Now, what we want to do is figure out how much of the boat's underwater. Is it floating? So we're just going to get a number for the boat. It's not super big. We'll say it's like 1.5 metric tons, so 1,500 kilograms. We can calculate the buoyant force from our equations we talked about earlier to be equal to the mass of the object times gravity, we can calculate the force of the boat to be just mass times acceleration. So 1,500 kilograms times 9.8 meters per second squared. We get that the force of the boat is 14.7 kilonewtons. Then we can calculate the force of the water. It's the same thing, 5,000 kilograms, that's the mass of the displaced water times gravity. We know that it's going to be times gravity because the force from the water will be equal to the weight of the water that was displaced, and weight is a unit of force. So we get that the force of the water will be 49 kilonewtons upward. 14.7 is obviously less than 49. So from that we can know that the boat is floating. If we want to know how much of the boat is floating, we refer to our volume density relation that we had earlier. So we have our volume of the fluid, we have our volume of the object, density of the object, density of the fluid. We can find the density of the boat, density object, by taking the mass, dividing it by the volume. We get nice 300 kilograms per cubic meter. And because we know that the density of water is 1,000, we can just equate that. We get a number, 0.3. That tells us that 30% of the boat is submerged and the boat is comfortably floating on top of the water. All right, so as we mentioned earlier, if the force of buoyancy is equal to the force of gravity, the object's going to be stationary in the fluid. If we want to find where it is, for example, if you have a block of some material, you put it in the water, it sinks to a given depth, and then it stays there. We want to find that height. It gets a little bit more complicated. The most important thing that we're going to need for this is what's called the bulk modulus. The bulk modulus is how the volume of an object changes as pressure increases. Because as the pressure on an object increases, it's pushing further in, the volume is going to want to shrink down a little bit. So here's a handy equation that'll give us the bulk modulus. We have our density equation. We know that the change in density can be represented as the negative mass over the volume squared. We know that the change in volume through some equation rearranging can be your negative density over change in volume divided by volume. And we know that the change in density divided by our density will be equal to the change in pressure divided by our bulk modulus. This is just some more equation rearrangement, but this is how we would end up solving for the height that something floats at. Our pressure equation is density, gravity, height. Our change in pressure we can represent as the same thing, because if we're looking at a system like this where we have some object and it sinks down to this depth, its initial pressure is going to be equal to 0. There's nothing above it. There's no column of fluid pushing down on it. So we can just ignore the initial pressure, and that just gives us our change in pressure. We take our density values, our pressure values, we plug it into these, we get our final minus initial times all of this. If we're given the bulk modulus of a fluid or an object, we can rearrange this with our known density values. Assuming gravity is Earth, we can rearrange this for h, and we'll be able to determine the height at which something is floating stable. We don't have time to go into all of that, but it is something that can be done.